Hey everyone, Doug here with Process Technology out of Salt Lake City, Utah. Question of the day, what defines a quality process analyzer transmitter? There's enough to talk about that I've broken this into three parts in the previous session, if you saw that, talked specifically about the form function. Let's get busy and dive into data integrity. Think about data integrity as a reliable, accurate, and robust measurement. Accuracy of a pH measurement begins with the sensor, but the transmitter design directly contributes to the displayed accuracy. Now, because the measured value is the sum of all the variables, which are the sensor, the cable, transmitter, well, then the accuracy is only as good as the weakest link. The transmitter, and more specifically the guts, are a large contributor to unreliability and inaccurate measurements. For example, there are still transmitters on the market with exposed printed circuit boards as shown here. This measurement board is processing an analog pH sensor input. It's literally sitting next to the power supply. Have you ever grabbed a sensor cable and seeing a shift in the reading when a motor or VFD kicks on? In many instances, the culprit is related to ground loops, panels not being bonded and grounded, or just bad, faulty power supplies. Keep in mind, 6 millivolts is equal to a tenth of a pH unit. That's 0.1 pH units. People control typically to 0.1 or 0.2 pH units. So 6 millivolts, clearly it doesn't take much interference to cause inaccurate measurements. A quality design transmitter incorporates galvanic isolation. Simply put, galvanic isolation is an elegant term for circuitry that completely isolates the pH input circuit from all other electronics in the system. Or you can think of it as disconnecting the sensor wiring from the system ground. Thus, it eliminates the effect of different ground levels. In the case of a pH transmitter, galvanic isolation is providing noise immunity. Again, we've all seen someone grabbing a sensor cable and watch the pH reading change. Or being told the pH shifts when the agitator or VFD kicks on, and that varies with the speed. Classic ground loop issues impacting the pH measurement. Again, 6 millivolts is equal to a tenth of a pH unit. Mettler eliminates this issue by incorporating galvanic isolation into their transmitters. Knowing ground loops are common and yet challenging to chase down and solve, Mettler also incorporates solution ground technology into their pH sensors to address common electrical interferences. Think of this as belt and suspenders, the belt being galvanic isolation and the suspenders being solution ground. Here's what we're talking about. This is a schematic of a combination pH sensor. pH lead wire right here, electrical potentials across the glass are measured, sometimes this is called the glass electrode, and the reference lead wire. These are tied to a transmitter acting as a voltmeter. Simply put, the pH measurement is the differential between the reference and the glass. For this measurement to work, the reference value here needs to remain stable, constant. If both of these variables are changing, how do you know what's contributing to the pH value? Now we have a bad agitator and a ground loop develops in the process. What just happened creates an electrical potential difference between the transmitter ground, should be this, and the ground potentials in the vessel, pipe, or even reactor. These ground currents will flow through the reference electrode and appear as a change in measured pH. So again, those potentials will travel through this circuit and essentially cause a change in our reading. In this example, a 0.2 pH change due to a ground loop that developed. This is not correct. Mettler solved this decades ago by incorporating an external platinum electrode that provides a true solution ground. In this schematic, the added ground current would flow through the reference and the solution ground, which would be shown here, traveling up through here. However, the circuit is intelligent to be able to see that the change is not from the glass electrode and thus isolates the pH value. The external platinum electrode is applied either as a dot or as a film. When wired properly to the transmitter, the solution ground helps to avoid disturbances caused by potential differences between the transmitter ground and the ground potentials in the process. A quality design transmitter incorporates both galvanic isolation and solution ground circuitry. About the same time as the first iPad, in case you don't recall, that was in 2009, which was actually before the first iPhone. At this point, Mettler took all of this to another level and rolled out true digital measurement from the sensor to the transmitter. This is the Digital Intelligent Sensor Management, or known as ISM technology, and has consistently solved issues. So to demonstrate this signal integrity data reliability, we've got a pH probe sitting in pH buffer 4. We're going to let that drop into a bucket of tap water. Essentially let this sensor now equilibrate over time. It reaches roughly a low 7 pH value. Then we're going to disconnect this probe and show that once the sensor is disconnected from the transmitter, the handshake that we saw in an earlier video, the transmitter recognizes there's no sensor, and eventually it's going to give dashes, which suggests that there's actually no data input to that transmitter. Now with the sensors and connectors still submerged, we're reconnecting it. We'll let that handshake occur, very quickly recognizes there's a sensor, and it should go back into normal operation, as we see here. And then we'll just sort of speed up the time frame here to let the sensor equilibrate back to the pH value which it started at, which was in the low 7s. Now, as an interest to see how it's performing when it was in pH 4 buffer, let's put it back into that. And let's let it equilibrate. So essentially, this is all about the integrity of the sensor connection.